Welcome back, my dear students. Last class we have discussed the assumptions in analysis of a singly reinforced section. So we will continue with the analysis of a singly reinforced section. Today you are going to see a new concept, that is the limiting depth of neutral axis. Limiting depth of neutral axis, it is denoted as XU limit or XU max. It is denoted as either XU limit or XU max. Now consider a singly reinforced section having effective depth small d, width b, and total depth capital D. It is reinforced with 3 bars. The area of steel, I will take it as AST. I will denote it as AST, that is the area of steel under tension. Now if I am drawing this strain variation or strain diagram, you will get a linear variation for strain having maximum of 0.0035 at the compression side and not less than 0.002 plus 0.87 Fy by Es at the tension side. We have a linear variation and the depth of the neutral axis when the strain in concrete and the strain in steel reaches its maximum simultaneously is called as the limiting depth of neutral axis or XU limit or XU max. That is, when the strain in concrete reaches its maximum as well as the strain in steel reaches its maximum at the same time, the depth of neutral axis is called as XU max. So I am going to denote it as XU max. XU max. So this distance is what? This distance is D minus XU max. This distance is D minus XU max. Now if I am considering the similarity of triangles, I could write D minus XU max by XU max is equal to D minus XU max by XU max is equal to 0.002 plus 0.87 Fy by Es divided by 0.0035. That is, D by XU max minus 1 is equal to 0.002 Es plus 0.87 Fy by 0.0035 Es. That is, D by XU max is equal to 0.002 Es plus 0.87 Fy by 0.0035 Es plus 1. That is, I could write it as XU max by D is equal to 0.0035 Es divided by 0.002 Es plus 0.87 Fy plus 0.0035 Es. Taking the value for ESS, that is the Young's modulus of steel as 2 into 10 raised to 5 Newton per mm square, 2 into 10 raised to 5 Newton per mm square. You'll get XU max by D is equal to 0.0035 into 2 into 10 raised to 5. That you'll get it as 700 divided by, in the new denominator you'll get it as 1100 plus 0.87 Fy. That is 1100 plus 0.87 Fy. Which means this XU max by D will only depend on the grade of steel being used. That is, for different grade of steel, the XU max by D will vary. So I could write it as, that is, I could say the value of XU max by D will vary according to the property of steel only. So for mild steel, there is your ms bar Fy is 250 Newton per mm square, and if I am fixing Es as 2 into 10 raised to 5 Newton per mm square, I could write, substituting this value of Fy as 250 Newton per mm square and Es as 2 into 10 raised to 5 Newton per mm square, 2 into 10 raised to 5 Newton per mm square. I'll get Xu max by ds. I'll get Xu max by ds 0.53. I'll get Xu max by ds 0.53. Now for HYSD bars, having yield strength Fy is equal to 450 Newton per mm square, and taking Es value as 2 into 10 raised to 5 Newton per mm square, and taking Es value as 2 into 10 raised to 5 Newton per mm square, I'll get Xu max by d is equal to 0.48. I'll get Xu max by d is equal to 0.48. Get Xu max by d is equal to 0.48. Now for HYSD bars having Fy as 500 Newton per mm square, having Fy as 500 Newton per mm square, and Young's modulus as 2 into 10 raised to 5 Newton per mm square and 2 into 10 raised to 5 Newton per mm square, I'll get Xu max by d. I'll get Xu max by d value as 0.46. I'll get Xu max by d value as 0.46. That is, I could summarize it as the Xu max by d values depend on the grade of steel being used. That is, for Fy 250 it is 0.53, for Fy 450 Newton per mm square it is 0.48, and for HYSD bars of Fy grade 500 Newton per mm square it is 0.46. You need to by heart these values, because based on this Xu max by d we will determine the type of section that we will study in the coming lectures. So you need to by heart these values for at least for ms bar, HYSD 415 and HYSD 500 grade steel. So that is based on the grade of steel. You have the Xu max by d value for HYSD bars. For mild steel bars, the value is 0.53. For HYSD bars having grade 415 it is 0.48, and for 500 it is 0.46. Now we have finished discussing the concept of limiting depth of neutral axis, or your Xu max. Now we are going to see the analysis of the stress strain curve. That is, you are going to see the actual depth of neutral axis and the moment of resistance of a singly reinforced section. That is, now you are going to see the analysis of stress strain curve of a singly reinforced section. That is, you are going to determine the actual depth of the neutral axis and moment of resistance of the singly reinforced section. So now, in order to do this, we will consider a singly reinforced section. Having effective depth small d, reinforced with 3 bars at the tension side. That is, we are having AST, area of tension reinforcement, as 3 bars at the tension side, having an overall depth capital D and width small b. Now if you are drawing the strain variation, at the level of concrete, you can see the maximum strain in concrete is 0.0035 and maximum strain in steel is 0.002 plus 0.87 Fy by Es. So this value is 0.0035. This value is 0.002 plus 0.87 Fy by Es. And here I will consider the depth of the neutral axis at some depth xu. That is a general depth of neutral axis. I don't know what is this value for xu. I need to determine this value for xu. Now we know if I am drawing the stress distribution for this singly reinforced rectangular section, I will get the value at the compression side as 0.446 FCK up to a strain of up to a strain of 0.002, it is a straight line. Up to a strain of 0.002, it is a straight line. Then it is varying parabolically. It's very parabolic. This you have seen in the case of your stress strain block or stress block of a concrete. You have seen the idealized stress block of concrete. So I'll divide this whole section into, I'll divide the section above the neutral axis into two parts, that is based on the strain variation from 0035 to 0.002 strain. I'll divide into one part, and the remaining part from 002 strain to 0, that is up to the neutral axis, I'll divide into another part. As you can see here, I have divided the rectangular portion into a red color part, and I have divided the parabolic portion based on the stress diagram into a blue color part. The compressive force is acting somewhere here. I need to determine the compressive force is acting somewhere here. I need to determine this value for this compressive force, as well as the point of application of this compressive force, the value for the tensile force, and all those things. So we are going to see those in this lecture. I am going to name this as A, B, C, D, E. So considering the triangle ACD and ABE, I can write 0.0035 by 0.002 is equal to AC by AB, isn't it? That is, I could write AB is equal to AC. What is AC? AC is the XU, that is the depth of neutral axis. That is, I could write XU into 0.002 divided by 0.0035. That is, you will get this value of AB as 4 by 7 of XU. You will get the value for AB as 4 by 7 of XU, and it's and you will get the value for BC as XU minus 4 by 7 XU. That is, you will get this value as 3 by 7 XU. This will get this value for AB, that is the parabolic portion, parabolic part as 4 by 7 XU, and rectangular part BC as 3 by 7 XU. Now we are going to see what is the compressive force and the tensile force acting on this rectangular section. For that I'll consider the same section. I'll consider the same singularly reinforced rectangular section, and I'll take the stress diagram. I will consider the stress diagram, which is having the tensile force is acting at T and the compressive force is acting at C. Now I will divide this into two parts that I told you, that I will divide the rectangular part and a parabolic part. Now the force acting on the rectangular part, I will denote it as C1 at a distance of y1, and the force acting at the parabolic part, I will denote it as C2 acting at a distance of y2 from the top. So if I write the compressive forces acting, I could write the compressive forces acting on the compressive forces acting on the beam of width B. I could write for C1 I could write it as the width into area of the stress diagram. Width into area of stress diagram. Here the stress diagram is rectangular. That is, I could write it as small b into area of the stress diagram here is what? 0.446 FCK, that is width, into the depth, that is 3 by 7 XU. That is, this value you will get as 0.191 FCK B XU, and this is acting at a distance of y1. There y1 is equal to, it is acting at a distance of y1, where y1 is equal to 1 by 2 of 3 by 7 xu. You'll get it as 3 by 14 xu. 3 by 14 xu. Similarly, you'll get the value for C2, that is the compressive force. C2 is equal to width of this section into area of stress diagram. Here the area of the stress diagram is parabolic. Here it is parabolic. That is, you'll get it as small b into the area of a parabola. You'll get it as 2 by 3 of 0.446 FCK into the distance is what? That is 4 by 7 XU. That is 4 by 7 XU. You will get this value as 0.1717 FCK B XU, and it is acting at a distance of y2. That is, you will get this y2 as 3 by 7 XU plus, because we are considering from the top, you will get it as 3 by 7 XU plus. For a parabola, the y bar distance is at a distance of 3 by 8 of your 4 by 7 XU. You will get this value as 9 by 14 XU. You get this value as 9 by 14 XU. That is, your compressive force C1 is equal to 0.191 FCK BXU acting at a distance of 3 by 14 XU from the top fiber, and C2 the value is 0.17 FCK BXU acting at a distance of 9 by 14 XU. So the total compressive force taken by the beam of width B, I could write it as C1 plus C2, that is 0.191 FCK B XU plus 0.17 FCK B XU. You'll get this value as 0.36 FCK B XU. That is the total compressive force. You will get this value as 0.36 FCK B XU. And now you need to find the line of action of this force. That is, you need to find the line of action of this force. I will call it as y bar. That is the distance of the line of action of the force C from the top compression fiber. I will get this value for y bar as C1 y1 plus C2 y2 by C1 plus C2. You'll get this value as 0.42 XU. You'll get this value as 0.42 XU. That is, the total compressive force 0.36 FCK B XU is acting at a distance of 0.42 XU from the top compression fiber. That is, I could write here this C is equal to 0.36 FCK B XU acting at 0.42 XU from the top compression fiber. That is, summarizing it, I could write the total compressive force taken by the beam of width B is equal to 0.36 FCK B XU at 0.42 XU from the top compression fiber. Now our basic assumption in the analysis of a single reinforced section was the total tensile force is taken by the steel alone. That is, the reinforcement is taking the entire tensile force. So the total tensile force, I could write it as the total tensile force is equal to 0.87 Fy, that is a stress in steel, into the area of steel, that is AST, that is 0.87 Fy AST. That is the total tensile force acting on a singly reinforced section. So if I am summarizing it, I am having a singly reinforced section having small d as the effective depth, small d as the effective depth, b as the width of the section, capital D as the overall depth. The strain in steel is 0.002 plus 0.87 Fy by Es. It is 0.0035, 0.002. We have divided this into two sections, that is up to a strain of 0.002 it is linearly varying, and then it is parabolic. So I could summarize here a single reinforced section having effective depth small d and width small b and overall depth capital D, reinforced with area of steel denoted as AST, having the strain distribution shown here, having the stress variation for the concrete and steel as shown here, up to a depth of 3/7 XU, it is straight, and after that is for a depth of 4 by 7 XU, where XU is the depth of the neutral axis. It is parabolic, and the total compressive force is 0.36 FCK BXU, acting at a distance of 0.42 XU from the top fiber, and the tensile force T is equal to 0.87 Fy AST. The tensile force is equal to 0.87 Fy AST. So I could call the distance between the line of action of these two forces, as lever arm. The line of action of these two forces as lever arm. And here the lever arm distance is what? Here the lever arm distance is d minus 0.42 XU. The lever arm distance is d minus 0.42 XU. That is the distance between the line of action of these two forces. Since the compressive force is acting at a distance of 0.42 XU from the top fiber, and the tensile force is acting at a distance of small d from the top compression fiber, the lever arm, that is the distance between the line of action of these two forces, is d minus 0.42 XU. So in limit state method of design, in order to determine the actual depth of neutral axis, in limit state method, what we do is we equate the total force of compression to the total force of tension. In limit state method, we equate total force of compression and total force of tension. That is, we'll equate C is equal to T. That is, your C is what? 0.36 FCK BXU, and your total tensile force is what? 87 Fy AST. So equating these two, I'll get the value for XU as what? 0.87 Fy AST divided by 0.36 FCK B. That is, the actual depth of the neutral axis in limit state design is obtained by equating the total compressive force and the tensile force, and that is equating 0.36 FCK BXU with total tensile force, that is 0.87 Fy AST. You'll get XU as 0.87 you'll get XU as 0.87 FYAST divided by 0.36 FCKB. It's very important. Now the next class we will discuss on the moment of resistance of a section. We will discuss on the moment of resistance of a section.